Today, we're going to follow the incredible journey of a single X-ray photon, from the second it's born as pure energy all the way until it becomes a single critical pixel in a medical image.
It's an amazing idea, right? That every X-ray image we see begins as something completely invisible. We're going to trace that energy from start to finish to really understand how we create these images that are so vital in medicine.
All right, welcome back everyone to the RadSound Radiology Physics Series. Today we're diving deep into the complete story of how an X-ray image is made, and we're going to figure out what makes a good X-ray, well, good.
So our whole story kicks off deep inside the X-ray tube. This is where a super high-speed electron slams into a metal target, releasing all its energy and creating a brand new X-ray photon. And just like that, it's off on its mission.
And that mission, it basically follows a four-step game plan. First, the beam gets created. Second, it has to travel through the patient and it gets weakened along the way. Third, the photons that actually survive are captured by a detector. And finally, all that information gets turned into the image we can actually see. We're going to walk through every single step.
Now for step 2. And let me tell you, this is where the real magic happens. Our little photon now has to navigate what is basically a gauntlet, the human body. And it's right here that the foundation of the entire image is laid down. The key physics principle at work here is something called differential attenuation. And that sounds complicated, but it's actually a really simple and powerful idea. Dense stuff, like bone, stops X-rays way better than less dense stuff, like muscle. That difference is everything.
And you can really see what I mean when you compare bone and soft tissue. When that swarm of photons hits dense bone, most of them get absorbed. Only a few make it through. That area shows up on the image as white, or what we call radio-opaque. But when those same photons hit softer tissue, a lot more of them just pass right on through, and that creates the darker gray and black parts of the image, which we call radiolucent.
So, the photons that actually make it all the way through the patient, we call that the remnant beam. It's not a uniform beam anymore. It's now carrying an invisible pattern, kind of like a shadow message, that holds all the information about the different things it just passed through.
Okay, on to step 3. We have to capture that message. The remnant beam, carrying all that precious information, slams into the image detector. The detector's whole job is to catch these surviving photons and turn their energy into a signal we can actually measure.
Now, the most important metric for how well a detector does its job is called detective quantum efficiency, or DQE. Honestly, you can just think of it as the detector's batting average. A high DQE means it's awesome at catching photons and doesn't waste any information. This is huge because it means we can get better images with less radiation.
And what's so cool is how you can see the technology evolve right here. Old school film systems, they were incredibly inefficient, wasting most of the photons that hit them. CR, or Computed Radiography, was a decent step up. But modern digital radiography, DR, is a total game changer with a much higher DQE.
Yeah, that's right, up to 70% efficiency. That means we can get an absolutely beautiful, high-quality image with just a fraction of the radiation dose that was needed just a couple of decades ago. It's a massive win for patient safety.
And that brings us to the final stage. The detector caught the photons, it generated a signal, so now let's see how that raw data gets turned into the millions of tiny pixels that make up the final image you see on the screen.
But, of course, there's an enemy in this process. There's always a villain, right? In imaging, that enemy is noise, specifically something called quantum noise. It's that grainy, kind of blotchy look you can get on an image, and it comes from a simple statistical problem, just not having enough photons to paint a clear picture.
So what's the big takeaway here? The relationship between the radiation dose and the noise is direct, and you just can't get around it. A low dose means you have fewer photons, which is going to give you a noisy, grainy image. To get a cleaner, clearer image, you need more photons, which means a higher dose. And the real art of radiography is finding that perfect balance.
Now, beyond just noise, we also care a ton about sharpness, or what we technically call spatial resolution. This is all about our ability to see tiny little details. It's affected by things like the size of the X-ray source and the pixel size in the detector, but also by something really practical: patient motion. I mean, you can have the best machine in the world, but if the patient moves, you've just got a useless blur.
So, all this physics brings us to the most important part of our journey. Why does any of this matter in the real world of medicine? Because this isn't just some academic exercise. It's about the art of literally seeing inside the human body.
So why does this photon's journey really matter?
It matters because every single step, from its fiery birth to its final capture, has a direct impact on our ability to make a confident diagnosis and actually take care of patients.
For a radiologist, it is a constant balancing act. We have to get an image that's clear enough to answer whatever the doctor is asking, but we absolutely must do that with the lowest possible radiation dose. And we have to be smart about it. We have to tailor our technique for the job. For example, we'd use low energy to get super high contrast for hand X-ray, but we need much higher energy to actually penetrate through the chest.
And this quote right here, it just perfectly sums up the modern way of thinking. It's not about just getting the lowest possible dose, because that might give you a useless, noisy image. It's about finding the right dose for the right reason, the dose that gives you the answer you need and nothing more.
And in the end, that's what this entire journey is all about. It's this incredible process of taking something completely invisible, a beam of energy, and through the precise application of physics, turning it into a visible truth that can literally save someone's life.